What are quantum dots? How do they work? What are they used for? And why was the Nobel Prize awarded for their discovery in 2023? We will sort all of this out in today's video. We will also have to deal with some extremely interesting concepts from the theory of semiconductor electronics, which I have already mentioned many times in our previous videos and kept promising to explain in more detail, but somehow never quite got around to it. By the way, I would like to take this opportunity to thank the sponsors of the channel here on YouTube, as well as on our Patreon and Boosty pages. Friends, it is precisely thanks to your support that I can devote enough attention to the channel and delight you with new videos as often as possible. And if you, my dear viewers, like what is happening on the channel and want it to grow and become better and better, I invite you to join the sponsors. The link in the QR code should now be on your screen, and all the necessary links will also be in the video description. And on this optimistic note, let us finally move on to the core of today's story, namely quantum dots. They are tiny crystalline particles, usually ranging in size from about 2 to about 10 nanometers, made of semiconductor materials such as indium arsenide, lead sulfide, and others. A single crystal can contain from several hundred to several 100,000 molecules of these substances. The most important feature of quantum dots is the following. Under the influence of external light, they themselves begin to emit light, and the wavelength of the emitted light becomes longer as the quantum dot itself becomes larger. Quantum dots with a diameter of about 2 nanometers glow blue. Those with a diameter of about 3 to 4 nanometers glow green and yellow, and those with a diameter of about 5 to 6 nanometers glow red and orange. As I have already said, classical quantum dots are tiny semiconductor crystals. And before talking about quantum dots, we need to recall how semiconductors themselves are structured at the atomic level. Ordinary conductors, which are usually metals, differ from dielectrics in the state of their electrons, more precisely, the electrons of the outer electron orbitals of atoms. In conductors, electrons are weakly bound to atoms, or rather, they are bound as if simultaneously to all atoms, roughly speaking, being attracted to them with approximately the same strength. The forces of attraction to different atoms mutually cancel each other out, and the electrons can move through the metal almost freely, remaining in a state of chaotic motion that is very similar to the motion of atoms or molecules in gases. That is why physicists often describe such electrons in metals using the term electron gas. It is this electron gas that comes into motion in an external electromagnetic field, ensuring charge transport. Therefore, these free, or more precisely, quasi-free electrons are called conduction electrons. In dielectrics, by contrast, electrons remain in bound states within atoms and cannot move anywhere. That is precisely why free charge carriers are absent in dielectrics, and these materials do not conduct electric current. Semiconductors combine features of both conductors and insulators. At room temperature, some of their electrons are in a free state, that is, they are conduction electrons, while others remain bound within atoms. At the same time, by supplying energy to an electron that is in a bound state in one way or another, it is possible to force it to break free from the atom. In other words, a semiconductor simultaneously contains both bound electrons, also known as valence electrons, as in dielectrics, and conduction electrons, as in conductors. Valence electrons are literally electrons located in atoms, and electrons in atoms, as we remember, can occupy specific discrete energy levels. However, this picture applies to isolated atoms. In semiconductors, as well as in other solid bodies and even in liquids, atoms do not exist in isolation, but are surrounded by many other atoms, which disrupts the familiar picture of electronic energy levels. The reason lies in the Pauli exclusion principle, which forbids more than 2 electrons from occupying the same quantum state. Let us imagine 2 atoms. Suppose that each atom has a certain electronic orbital filled. As long as the atoms exist separately, everything works fine. But when they approach each other so closely that their electronic shells begin to overlap, this situation can no longer persist. Their energy levels effectively become shared, and 4 electrons can no longer occupy the same energy level. At this point, a very interesting thing happens. The energy level splits, forming 2 new levels, one with slightly higher energy and one with slightly lower energy than the original level, and the electrons redistribute between them. If 3 atoms are brought together, the original level splits into 3 levels. if 4 atoms are brought together into 4 levels, and so on. In solid bodies, the number of atoms is extremely large, reaching millions and billions even in the tiniest grain of material. The atomic energy levels split into millions and billions of new levels, effectively forming a continuous band. These are still discrete levels, but the differences in energy between them are negligibly small, and therefore we can, in practice, treat them as a single continuous band. A similar situation applies to conduction electrons. To transfer an electron into this band, it is necessary to supply it with a certain amount of energy, the magnitude of which depends on the type of semiconductor and is determined by the width of its so-called band gap. However, we can supply the electron with a larger amount of energy, in which case it will occupy a higher position on the energy scale. In general, this energy can be almost arbitrary, and therefore, in a semiconductor, the existence of conduction electrons with almost any energy and momentum is allowed. As long as this energy is higher than the lower boundary of the band gap and lower than the energy required for the electron to completely escape from the semiconductor and fly away, that is the so-called work function energy. Thus, instead of the discrete set of energy levels familiar to us when we talk about individual atoms and substances composed of isolated atoms, a so-called band structure is formed in semiconductors. The term band here does not refer to some spatial region inside the semiconductor, but to a range of electron energies. Electrons with the lowest energies are located in the valence band, while electrons with higher energies occupy the conduction band. These two bands are separated by the so-called band gap, the width of which is determined primarily by the chemical composition of the specific semiconductor. As we have already discussed, it is possible to supply an electron in the valence band with enough energy for it to jump over the band gap and end up in the conduction band. In doing so, an occupied electron vacancy is formed in the valence band, which behaves like a positively charged particle called a hole. After spending some time in the conduction band, the electron undergoes a reverse transition. During this process, energy is released that is equal to the energy width of the band gap. If this width is sufficiently large, then this energy is often, though not always, released in the form of a photon, that is, a quantum of electromagnetic radiation. This effect is used in light-emitting diodes. In them, the transfer of electrons from the valence band to the conduction band is accomplished by the energy of an external electric field, while the energy of the reverse transitions is released in the form of quanta of visible light. This is not the only possible mechanism. One can, for example, direct a photon at a semiconductor crystal whose energy exceeds the width of the band gap. One of the electrons in the crystal will absorb this energy and transition into the conduction band. After that, the electron will gradually move downward along the energy scale toward the lower boundary of the conduction band. The excess energy in this case is released in the form of vibrations of the crystal lattice, essentially as heat. Such transitions are called non-radiative. The radiative transition, on the other hand, occurs from the lower edge of the conduction band, and the amount of energy released as a result is always the same for a given type of semiconductor. We can initiate such transitions using electromagnetic radiation of various wavelengths, and at the output we will obtain emission of a very specific color. This phenomenon is called luminescence. The width of the band gap, and therefore the color of the luminescence, is determined by the chemical composition of the semiconductor. If we want to obtain emission of a particular color, we must use different semiconductor materials. For red luminescence, aluminum gallium arsenide or gallium arsenide phosphide are suitable. For green luminescence, indium gallium nitride is used, and so on. The specific feature of quantum dots is that they make it possible to obtain different colors of luminescence, including the colors emitted by light-emitting diodes, without changing the chemical composition of the material, but simply by changing the size of the microscopic crystal. This becomes possible precisely because the crystals are extremely small. So small that the behavior of electrons in them begins to differ significantly from the behavior of electrons in large, macroscopic semiconductor crystals. Electrons in the conduction band of a semiconductor crystal can move almost freely throughout the crystal in all directions, over distances that are large on the scale of the crystal lattice. However, in a small crystal, this is no longer the case. Their freedom is rigidly limited by the boundaries of the crystal, beyond which the electrons cannot escape. And if in a large crystal, electrons spend most of their time moving in straight lines with approximately uniform motion, then in a microscopic crystal of a quantum dot, they constantly change their direction of motion, as if reflecting from the boundaries of the crystal and returning into its interior, only to collide with another boundary again after an extremely short time and reflect from it once more. At this point, those who have studied quantum mechanics have probably already guessed where this is going. This situation is extremely similar to the classic quantum mechanical problem known as the particle in a box. This problem is formulated as follows. There exists a particle placed inside a box with completely impenetrable walls and with an edge length equal to L. The question is, how will the particle behave in such a box? From the point of view of classical mechanics, the answer is, in general, obvious. The particle will fly from wall to wall, reflecting from them and performing something resembling oscillatory motion. If the box is very small, so much so that the situation must be described using the laws of quantum mechanics, everything changes. In a correct and rigorous formulation, the particle in a box problem is solved within the formalism of quantum mechanics using the Schrödinger equation. I will simply show this solution here on a single screen. Those who are interested can pause the video and take a look. The same solution to the particle in a box problem can be obtained by recalling a key principle of quantum mechanics, according to which the motion of an electron is described by the motion in space of a so-called probability density wave, representing the probability of finding the particle within a given volume of space. As this wave propagates inside the box, it will repeatedly reflect from the walls, interfering with itself in the process. A standing wave is formed, which is stable only if the nodes of this wave are located at the walls of the box. This means that an integer number of half-wavelengths must fit along the length of the box. This is a classic result, well known to us from acoustics and wave optics. That is, the de Broglie wavelength of the particle in the box may take one value or another or yet another, but wavelengths of other, incompatible sizes will not form stable states. The de Broglie wavelength is completely determined by the particle's momentum according to a certain formula, and the momentum, in turn, determines the kinetic energy according to another formula. From these expressions, one can obtain a corresponding expression for the possible energies of an electron in a box. L denotes the size of the box, and N denotes a certain natural number, 1, 2, 3, 4, and so on. That is, when we are dealing with quantum mechanical objects that propagate through space like waves, restrictions immediately arise on the possible values of their kinetic energy. As it turns out, this energy can take only certain discrete values that depend on the number n. Moreover, the smaller the box, the larger the spacing between the allowed energy values. For very large boxes, the energy spectrum becomes effectively continuous, whereas for small boxes, it splits into distinct spectral lines, with the spacing between them increasing as the box becomes smaller. By the way, we have already encountered this phenomenon of energy level quantization before. This is exactly how the energy levels of an electron in an atom appear as discrete. And this is not a coincidence. Just like a particle in a box, electrons in an atom are in a bound state, in the sense that they cannot leave the boundaries of a certain region of space. It is precisely this spatial confinement that gives rise to the discreteness, the quantization of the allowed energy levels, both for a particle in a box and for an electron in an atom. But in our quantum dot, as we have already discussed, electrons are also localized within a certain region of space, namely the region occupied by the dot itself. This means that they too cannot have arbitrary energy values. In a very small semiconductor crystal, the continuous energy bands are also split into discrete energy levels, and the smaller the crystal, the stronger this splitting becomes. And if in a large semiconductor, transferring an electron from the valence band to the conduction band required an energy that was roughly speaking equal to the width of the band gap, then in a quantum dot of nanometer scale size, this is no longer the case. Due to the splitting of the energy bands into discrete levels, the energy required for a transition into the conduction band increases. Consequently, the energy released during the reverse transition also increases, which is essentially the energy of the photon emitted The larger the crystal, the smaller the energy spacing, the lower the energy, and the longer the wavelength, until it finally becomes equal to the width of the band gap, and we return to the same luminescence wavelength that is observed in large semiconductor crystals. This is exactly how the dependence of the luminescence color of quantum dots on their size arises. Now that we understand how quantum dots are structured, let us look at how they can be useful to us. The first and most obvious application is the replacement of the light-emitting diode displays widely used today, such as OLED displays, with displays based on quantum dot light-emitting diodes, known as QLED, which promise improved image quality. Classical light-emitting diodes emit light during the process in which electrons jump across the band gap, and the energy of the emitted photons corresponds to the width of this band gap. The problem is that these jumps do not always occur strictly from the very bottom of the conduction band to the very top of the valence band. An electron can undergo an optical transition while still being somewhere inside the conduction band, and then land somewhere in the middle of the valence band. As a result, a classical light-emitting diode does not emit light at a single, strictly defined wavelength. The color is not a pure red, but appears somewhat washed out or dirty. Quantum dots do not suffer from this problem. They do not have continuous energy bands. Roughly speaking, an ordinary light-emitting diode is like a staircase from which one can jump down starting from almost any step, whereas a quantum dot is like a diving tower with a precisely defined platform height. And what is especially remarkable is that the height of this platform, and therefore the wavelength of the emitted light, can be tuned at will simply by changing the size of the quantum dot. This makes it possible to create purer and more natural image colors in a display. At present, QLED displays are already available for purchase in stores. However, these are not yet fully QLED displays, but rather hybrid designs in which quantum dots are used in combination with conventional light-emitting diodes. Each pixel consists of 3 subpixels, each made up of a light-emitting diode and a layer of quantum dots whose sizes are chosen so that their luminescence produces red, blue, and green colors. The light-emitting diode can emit, for example, ultraviolet radiation, which is invisible to the eye but activates the luminescence of the quantum dots. Due to the destructive effect of ultraviolet radiation on many materials, a different approach is commonly used today. In this alternative scheme, the backlight light-emitting diodes are not ultraviolet, but bright blue. In this case, the blue subpixel does not contain a luminescent quantum dot layer. The resulting colors are somewhat less pure, but the entire structure becomes more durable and less energy-intensive. An alternative approach is to make quantum dots emit light through luminescence driven directly by an electric current. In this case, the light-emitting diode is not built from a single large crystal, but from a multitude of quantum dots. So far, it has not been possible to implement this technology in practice. Electric currents tend to damage quantum dots and cause various other negative effects, which disrupt color reproduction or reduce brightness. These problems are not fundamentally unsolvable, but for the time being, truly pure QLED monitors based on electroluminescence exist only in the form of laboratory prototypes. Quantum dots have many other impressive applications, for example, in solar energy. We have a separate, extensive video on solar cells. Here, we will mention only the most important points. A photovoltaic cell is, in essence, a sandwich of N-type semiconductor material in which electrons dominate as charge carriers, and P-type semiconductor material in which holes dominate, that is, vacancies for electrons in the valence band. At the interface between these semiconductors, a depletion region is formed in which electrons and holes recombine, meaning that electrons return to the valence band. An internal electric field is created, directed from the N-type semiconductor toward the P-type semiconductor. When photons of light fall onto this sandwich, they can interact with the semiconductor material, initiating transitions of electrons from the valence band to the conduction band. The internal electric field drives the charge carriers in opposite directions, electrons toward the N-type region and holes toward the P-type region, where negative and positive charge, respectively, accumulates. If we now connect the ends of the sandwich with an ordinary conductor, electrons from the N-type region will flow into the P-type region. An electric current arises, and it is this current whose energy we can then use. In that same video, we discussed the key problem of modern solar cells, their efficiency of converting solar energy into electrical energy is limited. In essence, modern photovoltaic cells exhibit high efficiency only within a very narrow range of frequencies of the incident light, namely those for which the photon energy is approximately equal to the width of the band gap. If the photon energy is lower than this value, it cannot force an electron to move into the conduction band and create an electron-hole pair. But photons with excessively high energies are also not used very efficiently. They do create an exciton, but they place the electron far above the lower edge of the conduction band, from where it then gradually relaxes downward along a ladder of energy transitions, uselessly giving up a significant portion of its energy in the form of heat. In other words, in photovoltaic cells, the energy of high-energy photons is wasted. And if the macroscopic semiconductor crystal is replaced by a large number of quantum dots, this potential can, in principle, be realized. In a quantum dot, a high-energy photon cannot simply throw an electron far up into the conduction band because there is no continuous band there at all. Instead, there are discrete energy levels, and it is not guaranteed that the photon's energy will match one of them closely enough to cause a transition. However, it can transfer not one, but 2, 3, or even more electrons into the lower part of the conduction region at once. This phenomenon is known as multi-exciton generation. It allows quantum dots to utilize the energy of high-energy photons much more efficiently for the purpose of electricity generation. To make this work in practice, it is still necessary to find an efficient way to extract electrons and holes from a quantum dot before they recombine. Solving this problem is precisely what scientists and engineers are actively working on today. The effort is well worth it. According to even the most conservative estimates, solar cells based on quantum dots with multi-exciton generation could convert roughly 45% of the energy of the incident light flux into electrical energy, compared to about 20% today, more than doubling the efficiency of solar cells. Some researchers believe that the conversion efficiency could reach as much as 80%. Perhaps the most striking property of quantum dots is that they exhibit quantum mechanical behavior, such as discrete energy levels and related effects, at fairly substantial sizes. Yes, they are extremely small, but they are still many orders of magnitude larger than atoms. As a result, they are much easier to work with, easier to observe, and far more resistant to random external disturbances. This makes it possible to use quantum dots in so-called quantum simulators, in which scientists attempt to study the behavior of quantum mechanical systems. For the same reason, quantum dots are also a material on the basis of which qubits can be created, which are the key building blocks of quantum computers. Quantum dots may also prove useful for the quantum internet, thanks to their ability to perform so-called single photon generation. A single quantum dot emits exactly one photon at any given moment in time. Quantum dots support single photon generation only in a specific operating regime. They are cooled to extremely low temperatures and then irradiated with short laser pulses, whose wavelength is close to that of the optical transition. In response to each such pulse, the quantum dot emits a single photon. At extremely low temperatures, in a quantum dot, there are no electrons in the conduction region. All electrons reside in the valence region. A transition into the conduction region can occur only under the influence of an external perturbation, in our case, the incoming photons of the laser pulse. No matter how short the pulse is, it contains many photons. But the key point is that the quantum dot absorbs only one of them. The reason is that the absorption of such a photon and the promotion of one electron alters the structure of the energy levels of the quantum dot. This is due to ordinary Coulomb interaction between charge carriers. Electrons repel other electrons, holes repel other holes, and therefore the formation of a second electron-hole pair requires more energy than the formation of the first one. The laser is tuned precisely to the optical transition corresponding to the creation of the first pair. After this pair has formed, the energy of the incoming photons is no longer sufficient to induce additional transitions. The quantum dot stops responding to the incoming photons until the first electron returns to the valence region, emitting that very photon in the process. And if the pulse duration is on the order of the lifetime of the electron in the conduction region, which is usually on the order of nanoseconds, then single photon generation is achieved. Such photons are extremely important, not only for various scientific experiments, but also for solving certain practical tasks, for example, in quantum data transmission and quantum encryption, topics that we discussed in more detail in a separate video. And although the list of potential applications of quantum dots presented above is far from complete, it should already be clear that this is a highly useful and very promising technology. In our upcoming videos, we will continue to explore curious and fascinating physical phenomena to understand their nature and the laws governing their behavior, as well as how scientists and engineers manage to find, at times, very unexpected practical applications for them. That is all for today. I wish you all the best, dear friends, and I look forward to seeing you again very soon in our next videos.